Okay, I want to start by once again thanking and congratulating Spenta, and also expressing my excitement and enthusiasm for this amazing blackboard, which may well be the longest blackboard in the world. And somehow I have a hunch that Spenta was was behind it, and so I'm not going to have to erase. I just Okay, so I'm going to talk about a series of papers, the first of which is a 2D stress tensor for 4D gravity. And and then some subsequent work. This was a paper which appeared on the archive this September, and there have been 2 to 3 follow-ups since then. And I should list my collaborators, my students, Dan Kapak, Prahar Mitra, actually, who is from, originally from, came to us from TIFR and is going on to the IAS next fall, and Ana Reclario. And there was a similar paper that appeared very shortly after by Chung, Sundram, and De La Fuente. And then the development, they weren't really follow-ups were by Sabrina Pistarsky, myself, and Shuheng Shao, also at IAS. And then there's another one by Kapek and Reclario. These 2 papers appeared in the last week, I think. And there's one to appear by Angelika Nande and Monica Pate. Okay. So the basic idea is a kind of rethinking of the way we think about scattering amplitudes in 4-dimensional field theory. And everything I'm going to talk about today is their generic statements that apply to all abelian and gravitational theories in 4 space-time dimensions. Now, usually when we want to describe such a theory, we have a scattering matrix. And we characterize it by the scattering matrix. And what I'm drawing here is a picture of Minkowski space. And in Minkowski space, we start at what's called past null infinity. And in this lecture, because of the lack of time, I'm only going to talk about theories with massless particles, which start at past null infinity and end up, you have some scattering process where things start at past null infinity and they end up at future null infinity. Massive particles, there's a very beautiful story involving a hyperbolic anti-de Sitter slicing of Minkowski space, but I won't have time to go into it. And so this is how we think about the scattering problem, as maps from past null infinity to future null infinity. And we usually work in terms of momentum plane waves. But there's a kind of different way, and it's just a sort of trivial rewriting. Up at null infinity, there's a sphere, and I'm going to use z and z bar as coordinates for the sphere. And these people introduced a nice name for this sphere. They call it the celestial sphere. We see when we look up in the sky, and we can think of all scattering amplitudes, there's nothing deep here, it's just a rewriting, as a correlation function on a 2-dimensional sphere, in which we have insertions of operators, some which are ingoing, some of which are outgoing, O1 to OK. And And these operators are labeled by, of course, their position on the sphere, ZZ bar, or ZK bar, as well as other quantum numbers which I'm suppressing, like their energy, which would be positive for an outgoing particle and negative for an incoming particle in my conventions. And, you know, they could have charge. In fact, they will have charge in this talk. And so we could just rewrite things in this way. The position of the sphere is the direction of the momentum, and a little later I will write down an explicit formula for that. Now, yes, so among the quantum numbers, this is an interesting, important point, but my answer to your question for now is among the quantum numbers, like the charge and so on, that I'm going to associate with this particle, is the energy omega. So I'm treating that as an extra dimension. But there's, of course, a continuous spectrum. Now, Lorentz invariance acts on this sphere as z goes to az plus b over cz plus d, where AD minus BC are complex numbers that equal 1. In other words, Lorentz invariance acts on the celestial sphere in the same way that global conformal invariance acts on the sphere in a correlation function in a two-dimensional field theory. Now, I think everyone in this room, the minute they see the global conformal group, they say, where's the local conformal group? And indeed, there's a theorem in two-dimensional field theory that if you have the global conformal group and various others, discrete spectrum, various a few other assumptions, you automatically get the local conformal group. So is there a local conformal group at action here? And the answer is, in a sense, which I'll make precise, yes. And what happens is that, and I guess that's what I will try to explain here. And what happens is, when you turn this, if you take whatever quantum field theory you're talking about and couple it to quantum gravity, there is a local conformal symmetry. And what we did in this paper, and what Chung et al. Did, is construct explicitly an operator, which we call TZZ in an obvious notation, out of modes of the graviton, which has the property that its insertion in this correlation function, or in the old language, it's, if you add it to the asymptotic state, has the property that it obeys all the ward identities of a stress tensor in a two-dimensional conformal field theory. Now, let me make at the beginning some sort of caveats, which I'll come back to later. What we have done so far is analyze this operator, which I'm going to construct, single insertions of the operator. And it's going to be related to a soft theorem that Cacciazzo and I proved a year or two ago. The question of multiple soft insertions of gravity is a still unsolved problem. Not a very hard one, but not many people looking at this. And that would have to be solved to understand whether they're one of several questions that would have to be answered to determine whether there is a central term present. There are also one-loop corrections to what I'm going to say, which I will talk about at the end. So what I'm saying now is true at tree level. But finally, the most important thing I want to say is that okay, so if you have a quantum field theory that can be coupled to gravity, then its correlation functions, if you couple to gravity, you have a conformal field theory with a stress tensor. But if you just take the quantum field theory itself before you've coupled to gravity, it's like a subset of a two-dimensional conformal field theory. Its correlation functions, its scattering amplitudes, are like a subset of those of some kind of two-dimensional conformal field theory. But the kind of representations which appear are probably not the kind that we're used to, that we've been studying for the last 40 years in ordinary two-dimensional conformal field theories. They very likely have imaginary conformal weights that appear in, that are continuous. Nevertheless, these are certainly well-behaved theories because S dagger S equals 1 is some statement about these correlation functions. It's just a different kind of unitarity than we're used to discussing about in ordinary two-dimensional conformal field theory. Okay, so I kind of sketched where I was going, and let me now actually write out some equations. So in general, in quantum field theory, we write scattering amplitudes as matrix elements of the S matrix between out states and in states. Now, let me consider a, let me write AN plus 1 of Q as the same scattering amplitude where one adds to the outgoing state a graviton with momentum Q, and for simplicity, I'm just going to write out the formulas for negative polarization. Obviously, there's a similar one with positive polarization. And now there's a theorem that for small q, that this is equal to S0 minus, which goes like 1 over q, plus S1 minus, which goes like q to the 0, plus corrections of order q, times the same amplitude times this AN. This pole was derived by Weinberg in 1965. In other words, if you take any scattering amplitude and you add to it a graviton, you let that graviton become soft, that is, you let its momentum go to 0, that the resulting amplitude has a pole in it, and it has a very universal, there's a very universal formula for S0 minus. It's the sum over all particles, k equals 1 to n, of pk mu. I'm writing now in momentum space, pk nu, the polarization of the graviton divided by pk dot q. So if you add this soft graviton to leading order, you get 1 over q times a number, the famous soft factor. Well, sorry, the 1 over q is here. The famous soft factor times the original amplitude. Okay, so about a year or 2 years ago, Cacciazzo and I discovered that the subleading term is also universal. And in fact, there's universal character to the first 3 terms. I'm not going to discuss the 3rd term. So the subleading term is similar, S1 minus, and it's equal to, I'm setting 8 pi times Newton's constant equal to 1. Again, you have a sum over all external particles, k equals 1 to n, of, this is a negatively polarized, epsilon mu nu minus pk mu q lambda jk lambda nu over pk dot q. So this looks a lot like the leading term, except we've taken this pk nu and we've replaced it with q contracted with the angular momentum of the kth particle. So this was the momentum of the kth particle, and this represents the angular momentum of the kth particle, which has both an orbital and a spin piece. The theorem says that they have to be there. Both have to be there, the orbital and the spin piece. Now, there's an important check on this formula that if you shift the graviton polarization by anything proportional to q, you better get 0, because that should decouple. And it turns out that if you do that, if we write epsilon minus mu nu is equal to any function of q times q nu, we get something which is proportional to the sum of the external momenta, which is equal to 0 by angular momentum, by energy momentum conservation. Here we get a similar result where this consistency of this formula is guaranteed not by momentum conservation, but by angular momentum conservation. So it's the same kind of formula, but it's coming not from momentum conservation, but from angular momentum conservation. Okay. Now, what is our next job? So our next job, this is kind of a weird looking formula, and I've written it in a plane wave basis. But now I want to think of scattering amplitudes and gravity as correlation functions on a sphere. So I want to rewrite everything in terms not of plane wave, not of things that are momentum eigenstates, but of things that are coming out at a point z on the sphere. Okay? And to do that, I have to introduce some coordinates. So let me introduce retarded coordinates for Minkowski space. So here we have retarded time u, and then we have a sphere here at null infinity, which we're labeling by z bar. And in these retarded coordinates, the metric and flat Minkowski space is minus 2 du dr plus 2r squared gamma zz bar dz bar, where gamma zz bar is just the round metric on the unit 2 sphere. And you can show that if you do this, that as I think it was Shiraz asking me a second ago, that in these coordinates, we can identify a q by the point it goes to on the sphere, and you find the map between the q's, which are in this momentum plane wave basis, and the points on the sphere looks like omega 1 z plus z bar over 1 plus z bar. I'm really just writing this out to show you that it's all completely explicit, over 1 plus z bar, and then 1 minus z bar over 1 plus z bar. So using this and similar formulas for the p's, we can just rewrite this. And it's a lot of algebra. But we can rewrite this soft theorem here. We can rewrite this soft factor as some function which acts naturally on this sphere. Okay, so what is it? Well, I'm not going to go through all that. What we find is that S1 minus, we've still got the sum there, one term for every particle, and it works out to be z minus zk squared over z bar minus z bar k times 2hk over z minus zk minus dzk, where this is the covariant derivative on the sphere. So if we rewrite things in terms of these natural coordinates for thinking of scattering amplitudes of coordinates on the sphere, we get that a soft photon insertion acts like this. There's one term for every particle. And what is this hk here? This hk is, hk you should think of as the L0 eigenvalue of, well, hk plus hk bar is L0 plus L0 bar, and hk minus hk bar is L0 minus L0 bar. So if we have a particle coming out at a point on the sphere, there is a unique decomposition of SL2C into our familiar L0, L0 bar, L bar 1, L1, and L bar minus 1, L minus 1. So this L0 plus L0 bar is the thing which is boosts towards this point, which leave it invariant. And then L0 minus L0 bar is the one that leaves these points invariant. And so this, if you like, is the conformal weight minus the twist of the particle coming out at this point. Okay, so that's the formula that you get. We can write it a little more explicitly as hk is equal to the spin of the kth particle times a half minus its energy d by its energy, and h bar k is the same thing with a minus sign in front of the spin. Okay, good. Now, this is the right-hand side of the formula of this soft. This is the thing that appears on the right-hand side of this soft formula. There's also the left-hand side. And how do we describe the left-hand side of the formula? Well, we're doing quantum gravity, and the metric is fluctuating. What did that mean? 5 minutes? Okay. We're doing quantum gravity, and the metric is fluctuating. And so we have extra terms here which look like plus RCZZ dz squared plus complex conjugate, which represents the gravitational waves. And so now, since I'm out of time, but I can sort of write down the final answer, which is 3 or 4 pages of computation. If I define the following thing, TZZ is equal to the integral d squared w I over z minus w dw squared dw bar integral from minus infinity to infinity du u du of CZZ. So this is a definition. This is a certain mode, a certain soft graviton mode. And it's a soft graviton mode. This u du projects out the pole. So it's a soft graviton mode which sees only the subleading term in the theorem. And you can show, using the identities that I've written here and massaging them around, that if I have that the soft theorem can be rewritten as TZZ O1 to On is equal to the sum from k equals 1 to n of hk over z minus zk squared minus or plus 1 over z minus zk squared covariant derivative on the sphere d dzk of this same matrix element O1 Z1 to On OK ZK. So to say that again, there's a certain mode of a soft graviton operator which has the property that if I insert it in any S matrix element, that it obeys all exactly, I'm hoping that you all recognize this Ward identity. It obeys exactly on the nose the Ward identity of a stress energy in a two-dimensional conformal field theory. So this brings into a new form things which people have been saying for 10 or 20 years now about superrotations and Virasoro symmetry and so on in quantum gravity, and puts it into exactly the form that we think of it in two-dimensional conformal field theories. Okay, so that's what we showed in that paper and which Chung and Sundaram also showed. Let me just briefly mention 2 things. That was in September. Some things that have happened in the last 3 months. Would you like to ask a question now, or should I finish? Okay. So now, it's known that this soft theorem, it was shown by Zwieburn and friends, that this soft theorem that Cachazo and I proved has an anomaly which is 1 loop exact. And so the meaning of that anomaly has been puzzling. We don't know what it means. But in about a week ago, we showed, so the anomaly has 2 pieces. It has a divergent piece, which goes to, diverges not in the UV, but in the IR. Anomalies are related to IR divergences. It has a divergent piece, and then it has a finite piece. The divergent piece has a universal form which can be written down in a very general way for almost any theory. So we showed that that divergent piece can be eliminated by a one-loop renormalization of TZZ. In other words, we can add to this a quadratic term which exactly cancels, and this required a lot of what seemed to be miraculous cancellations. My students went on for pages and pages, and then all of a sudden everything started canceling, and there it was. So this, the divergences can be shifted away. The finite piece is we haven't dealt with. In all known examples where it's been calculated, it actually vanishes. So in all those examples, there are no, this is an exact statement to all orders in perturbation theory, but there doesn't seem to be any reason to believe that this finite term is always going to vanish. And I'm not an expert on this subject, and so I don't know what to say about the finite pieces. That's an open question. The second thing I want to say is that recently, since it just follows from sort of very general arguments that we can think about 4D scattering amplitudes as correlation functions in a two-dimensional conformal field theory, why don't we see formulas like if we do a three-point function, why don't we see formulas like 1 over z1 minus z2, some number here? Why don't we see formulas like this? And there's one more term here. Why don't we see formulas like this when we do some three-point scattering amplitude of three scalar fields? Well, the reason we don't see formulas like this is we always work in plane wave bases. And plane wave bases, one plane wave is mapped into another plane wave by a Lorentz transformation. And so what I recently did in my paper with Pistersky and Shao is looked at massive scalar fields, and instead of using plane wave, we used highest weight representations of the conformal algebra, and indeed the calculations turn into Witten-like diagrams and a hyperbolic slicing of Minkowski space, and we got an answer like this. In general, the calculations can be very hard to do. Witten diagrams are not always as easy to evaluate as momentum space Feynman diagrams, but at least in one example, we showed that you get exactly an expression like this with some crazy ratio of gamma functions up here. And so one would like to go on and more generally explore this relationship between 4D scattering amplitudes and 2D conformal field theories. Of course, the existence of this infinite dimensional group in two-dimensional conformal field theory has led to the possibility of doing all kinds of controlling two-dimensional conformal field theories in almost unimaginable way. So I think it's a very exciting thing that this same group, even though the kinds of representations are different, are appearing in four-dimensional gravity. And so we would like to understand what the relationship is between the usual way, plane wave way of looking at things and looking at things as conformal field theories. So one of the theorems that has been proven, and this is hopefully soon to appear within the next few months with Angelika Nande and Monica Pate, is there's something that's been proved in abelian gauge theory in the last 10 or 20 years, the so-called soft factorization theorem. And it says that the S matrix in QE, any abelian gauge theory, has the form of a hard S matrix and a soft piece, and where this is the piece below some infrared cutoff and this is the piece above some infrared cutoff, and this contains all the collinear and soft poles. Now, you've seen something like this in two-dimensional conformal field theory. And that is that if you look at the correlation functions, O1 to ON, in OK, in a 2D conformal field theory, and this soft piece here contains arbitrary numbers of Wilson lines and arbitrary numbers of soft photons. And 2D CFT with a U1 current algebra, which in this map, there certainly will be a U1 current algebra. Whenever you have photons, you will have a U1 current algebra in the corresponding conformal field theory. These can be written as correlation functions of the so-called parafermions, which are all the these operators. You construct a U1 boson, you stripped off the charge, and that these factorize into the correlation functions, factorize into a current algebra piece, which you can compute using symmetries in a very universal way, and a much more complicated hard piece. So what we've shown, though with a little bit of hesitation because we're a little unsure of some of the integrals, is that these two statements are exactly the same. In other words, that there is current algebra, just like here, I got a stress tensor. When you have a U1, you can get a current algebra, and there's a current algebra in which we could compute exactly the soft part of the S matrix in QED. So let me conclude just by saying that clearly there's a very explicit connection between those theories in which we are most interested. The real world, which contains a billion gauge theory and contains gravity, that there's a deep and mathematically powerful connection between that and those theories which we can most control, namely two-dimensional conformal field theories. And we've made some progress in understanding the details of how that works.
Questions?
Oh, okay.
The soft theorems, sorry, I don't know much about this, but the soft theorems seem to have the following, just in scattering amplitude, seem to have the following structure. And please tell me if this is right. That there's some actual scattering happening, which is unaffected by these soft gravitons. And then after you scatter, you've emitted things that are almost on shell, and those almost on shell things interact with the soft gravitons. Is this right? And the soft factors are all associated with the propagation of these almost on shell things away to infinity.
Right.
Okay. So
poles.
Yes.
Yeah.
So it's then these soft theorems seem to be answering the question of what the true scattering eigenstates are. Right? It seems like this factorization that you're talking about divides up scattering into the real scattering, and the stuff that the issue that what you were scattering were not really eigenstates of the Hamiltonian because they keep emitting these soft particles. I was wondering whether one way of thinking of what you're doing is to be diagonalizing the free Hilbert space, so you're scattering the right things.
I would hope that is true, and you've given me an opportunity to say that I, before I get smashed by the, okay, you've given me the opportunity to say that I think there is a huge white elephant in the room of quantum field theory, which is that the S matrix doesn't exist because of infrared divergences. And it's clear that these symmetries, are related. They control the infrared structure. And there was no hope of understanding the infrared structure of quantum field theory without understanding these symmetries. And so I'm hoping that there will be some nice way to put this together when we,
I have one quick follow-up. You're looking at the situation where the infrared dynamics is free in the IR. But there are even more interesting, because you're looking at gravity or QED. But there are even more interesting situations in which you're doing scattering in conformal field theories, like n equals 4 Yang-Mills, where the structure of what you're scattering becomes even richer. I was wondering whether there would be, whether these ideas could extend in a non-trivial way to those situations.
Well, that is a very good and very important question, and I think that the answer is yes, though we haven't shown it, and it's related to the issue of loop corrections, because there is in n equals 4 Yang-Mills, at tree level, there is a soft gluon theorem. And instead of a U1 Kac-Moody, there's a non-abelian Kac-Moody. Again, I believe that at least at tree level, the soft factor in non-abelian gauge theories can be captured by this current algebra. But as you say, there are loop corrections, and at long distances, the soft theorem in non-abelian gauge theory, even the pole gets renormalized. That is why, thousands of papers on the S matrix of n equals 4 Yang-Mills, which is a thing that doesn't exist. This is a problem we should understand. What is the S matrix in n equals 4 Yang-Mills? One of the big efforts of our community is to understand quantum field theory, but we should at least have some vague idea of in what sense it exists. Okay, so the S matrix in n equals 4 Yang-Mills does not exist. I actually think, oddly, that this is going to be, some things are easier to understand in gravity. And I think, oddly, this question of what happens to the one loop corrections in gravity is a little more manageable than what happens in gauge theories that run at long distances. Certainly, I'm assuming there's some kind of infrared fixed point that, yeah.
One more question, and let's discuss.
This is sort of a free question, but do you have anything to say about other dimensions?
Yes. After all these years, I'm very happy to be in 4 dimensions. No, that is one of the things. This story, it's different in non-abelian gauge theory, it's different in abelian gauge theory, it's a different gravity. There are certainly soft theorems in every dimension. And there are many soft theorems. There are the interesting, in supergravity, there's a whole supermultiplet of soft theorems. And every one seems to have its own different intricacies. I have written a number of papers of limited scope about soft theorems and symmetries in higher dimensions. I'm not completely sure what the right way to think about them is.
Oh, but it's not just a CFT in d-2 dimensions, or at least has that symmetry? I mean,
Well, certainly the symmetries match. So it should be a CFT in d-2 dimensions. And since you mentioned that, another maybe unwritten statement is that the hope here is, in addition to finding a better way of thinking about quantum field theory with massless particles that don't exist so far, is how we think about flat space holography. And indeed, the idea is that holography in Minkowski space, what the first hint of holography was the matching of symmetries. And physics in Minkowski space matches with the conformal symmetry in 2 Euclidean dimensions lower. You kill one space and one time dimensions. So if this works, it's possible. The pipe dream is that we can independently define a conformal field theory on a sphere. And that conformal field theory computes for us the 4-dimensional Minkowskian gravity. So the pipe dream would be that that would be true in every dimension. It's kind of a different paradigm for holography than what we've been used to. Sorry.
Let's thank Andy.